Yeah, so at the very end of the plant, we have what is known as a Merrill-Crowe circuit. And that's actually a very conventional way of recovering, or if you like, not refining, but recovering gold and silver values such that we can then basically sell it as a commodity to a refinery. At this point, we've mixed fine zinc powder to produce a highly concentrated gold silver sludge. So essentially, we have a material which is really just zinc, gold, and silver. And by this stage, it's so concentrated that it's just really a few kilos a day. Then this goes into a heating type process, which drives off the zinc and also separates the gold from silver. The gold will still be contaminated with very small amounts of silver and potentially other metals, perhaps lead, for example, and that's why it will be sent to a refinery, which is quite normal, to produce the gold, which then goes on to the gold market. So the heating system that we use, because it's only a few kilos a day that we're dealing with, we have basically an oven with a fume extraction system, and the size of it is really no bigger than what you'd expect to find in, say, the kitchen of your downtown restaurant. So it's only handling a few kilos a day, and a proper fume extraction system, as I say, what you'd find established with a kitchen in a restaurant. So that's really the end of the process that we have on site for managing the gold and silver and separating as best as we can before it goes to the refinery. Yes, so generally we're dealing with quite dilute solutions, a lot of water, and it's really essential at the end of our system that we capture as much water as we can, clean it, and reuse it. And by doing that, it minimizes the amount of fresh water that we need to add to our process. So we use very cheap limestone powder to basically clean up the water so that we can reuse it. And when we do that, we produce a benign sludge or solid waste, which is largely composed of gypsum and ferric hydroxide. So quite benign, and that's what we dispose of. If small amounts of toxic elements are present, and that includes elements like arsenic, which we're very good at treating, those will also report to that sludge. And the arsenic is in relatively low amounts, but it is environmentally stabilized because the arsenic actually attaches itself and is captured by the very large amount of gypsum which is present and ferric hydroxide. And chemically, we produce what is known as a ferric arsenate. And when we look at doing stability testing on this, it very easily meets the US EPA approval using a method known as TCLP, toxicity characteristic leach procedure, and it is environmentally benign. And it's been shown that this type of waste is stable for 30, 50 years. When we look back at previous bioleach projects, that material is incredibly stable. But as I say, the majority of the waste is just a gypsum plasterboard type material with ferric hydroxide, which basically is like a sponge which holds other elements within it and is environmentally stable and extremely safe. So as I've mentioned before, as depletion of oxides becomes more common in the world and the world's supply of metals becomes more dependent on treating sulfides, then bioleaching itself will become more popular in its application. But it's not a panacea for treating everything, and we recognize that. But it is a proven technology which has now been in commercial application for about 40, 50 years. So it is a proven technology, which what we're looking at doing is basically expanding the type of applications in which we can use bioleaching. So it is relatively common to find it as the most economic and environmentally friendly method for treating refractory gold and silver sulfides. And it will become more common in treating base metal sulfides, which includes copper, cobalt, and nickel, and all of the elements which are needed for example, EV battery manufacturing. So undoubtedly, bioleaching will become more common. We've also shown that it's extremely good at treating toxic elements in an environmentally responsible and economic way. So we firmly believe that yes, there will be a lot more applications of bioleaching in the future, but it is not a panacea for treating all types of sulfides. Yes, so really what I want to do is just explain this very briefly from the technical point of view and give you comfort that basically, technically, it's relatively easy to expand a plant. Let me give you an example of a project that we had in China for toll treatment of concentrates. And that was established for treating a few tens of thousands of ounces per annum of gold concentrates from all over China and actually from other parts of the world as well. And it worked extremely well. And so within a couple of years, we were able to expand the capacity of that plant. And we did that relatively simply because basically it's a modular type process. So we can just add extra tankage to expand the process. And there needs to be obviously some expansion of downstream processing as well. But the majority of the space, if you like, of the process is occupied by the bioleach tanks. And we can easily expand that capacity by putting down extra pads and building extra tankage. The design of the existing plant, we also put some flexibility in that design so that, basically there may be opportunities to treat more ounces than its actually boilerplate target. But as I say, expansion of the plant is relatively easy up to a certain extent just by adding extra tankage. I think I should add that really by establishing this initial plant at 31,000 ounces, what we're doing is making a commitment, and we're saying to local miners that, look, here is a process that can treat your concentrates in an environmentally friendly and economic manner. It's a bit of a chicken and egg situation. So once we have that plant established, then more concentrates will become available as miners can see that we've made a commitment to treat their concentrates, and then that will allow expansion of the facility. So it's really a question of building the initial plant, which will then allow more concentrates to be sourced, which will then allow for the expansion of the facility.